your skills with the electron configuration here real quick. So if we go, you guys can still see my screen, right?
Yeah.
Good. Okay, so let's say we're talking about, let's write the electron configuration for this guy. Nickel 2 plus. What would be the electron configuration for that? Somebody cooking? No, thank you. Okay, electron configuration. Where do we start?
I'm just kind of sorry. I think someone was talking before me.
Okay, you're saying 1s.
1s2.
1s2. Okay.
And then 2s2.
Okay.
And then 2p6.
2p6.
Three S2.
3s2.
And then 3p6. Well, how about someone else? I don't want to hog like this entire Zoom meeting, so how about someone else does it?
Okay, what's after 3p6?
4s2.
4s2. And then? So we're at 4s2. That gets us down here.
Will it be 3d8?
Okay, so that would be for nickel, right? So if we were just talking about nickel alone, that'll be 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what happens when we remove 2 electrons is that you take from the largest period first, and then you work your way down. So what would be the largest period? Which one is the period that we use? What number? The front number or the subscript number? Are you there? Okay, fine. Then I'll ask questions of people since nobody's gonna. Alan, help me out.
No, I'm not sure about this. I don't think I was here on Wednesday.
Ah, okay. Jennifer?
You said to, can you repeat the question one more time?
So where am I going to take away? Because we're losing 2 electrons. That's what the 2 plus means, right?
Yeah.
Okay, so if we're losing 2 electrons, we're doing electron configuration. That means that we're going to be removing 2 electrons.
Yes.
Where do you think the 2 electrons are going to come from?
I'm not sure. I've always had trouble with this part of chemistry.
Okay.
Would it be the outermost orbital, which would be 3D?
Nope. So it wouldn't be the 3D. It would actually be the
4s.
4. Yes, the 4S.
Oh, okay, yeah.
Okay.
I didn't
so
see that in there.
The way it works is that there's two things that I want to point out to you guys. One of
Okay.
the things is, why aren't you guys using the core? So using did we talk about? I'm pretty sure we did. It's hard to remember. So many classes, they all kind of blend together. I'm like 90% sure I showed you the shortcut way. You guys remember the shortcut way of writing this for
The
nickel?
condensed version? I don't
Yeah.
think you did that last time.
Okay, so we're going to do it right now. So let's say we're just going to talk about nickel, and then I'll show you the ion itself. So if we have nickel, the compressed way of doing it is by finding the core. So what you use as a core is the noble gas. That's right before that. So that core means that you have all of the electrons that noble gas has, and then all the electrons that would be left over are considered to be your valence electrons. So your valence electrons are the ones that you're going to be using to interact in terms of chemical reactions. So in this case, we have nickel is right here. You guys see that?
Mm-hmm.
What is the atomic number?
28.
28. So you guys know exactly where nickel's at. So if you go to the noble gas that is before you get to nickel, the one that's right before you get to nickel, which
Argon.
noble gas would that be? That'll be argon. So you're going to use argon as your core. Okay, so that means we're saying that this element has all of the electrons that argon has, plus whatever's after that, right? So that means it's representing all of these right here. So that's what the argon is representing, okay? So then all you'd have to write then is your 4s2. (3d8).
Okay.
Now, doesn't that save you a lot of time?
Yes.
Okay. Now, so the 4s2 and the 3d8, so these are the electrons that are accessible for bonding or removal, okay? So then, in this case, since we're talking about nickel 2 plus, I'm going to write it the same way. So Ni and then 2 plus. I'm going to use the condensed version. So when you're removing electrons from an element, you want to take it from the highest period first. So this represents your period. Remember, these are your periods. That 4, that's where that 4 is making reference to. That 4s, s right here. You guys remember when I drew the s orbital here? Remember that?
Yeah.
So we're going to take from this first. We're going to take 2 electrons from there. So then all we're going to be left with is 3d. So this tells me that this element is an ion, for one thing, and it's this element is an ion because it's 2 plus. We've lost 2 electrons, and that right now we only have the 3d8 to play with. Okay, so the reason why that we do electron configuration so that we can kind of understand what's going to be happening with bonding, right? And so, and where electrons are at, you know, because we'll be giving them specific addresses to know where every electron in that atom is at, so that we can know what it's capable of doing. Okay, you guys get that?
Yeah, and I have one question. So if we go back to the original electron configuration, we take away the 4s2.
Yep.
Okay.
Okay, so you guys can see the distinction between the two? Yeah,
I
no,
have
maybe?
Yes.
I have a question.
Okay.
For the 3D,
Uh-huh.
if it's in period 4, why is it 3?
Because the way it works is the way the periodic table is organized. It's organized upon energy level. So this guy here, so you start your 3D at this point.
Okay.
Okay. Your 4F is going to start right here.
Energy. Okay.
Yeah. It's all about energy, right? So what we know is that in terms of energy, right? Because you want to put your electrons in so you keep the lowest energy level as possible. Well, 4s is actually a little bit lower than the 3D, so you fill up the 4s first, and then you fill up the 3D. But the funny thing is that since the 4s is on the outer shell, even though it's lower, it's still on the outer shell, it gets pulled away first. Okay?
So S gets pulled away first before
Yep.
D. So then 4S has a higher energy level than 3D does.
That's right.
Okay, thank you.
Yeah. So I'm going to show you a couple of figures because I think I skipped over some things with you guys, or we didn't get to them and I thought we got to them. So that's the problem again about having so many classes that they all kind of blur together. Okay, so I'm going to share my slides real quick. Then we'll try another problem. Okay, so this basically just shows you the energy that's associated with it. So you have your 3s, you have your 3p, then you have your 4s, then you have your 3d. So that's showing you in terms of increasing energy level. So since it's in terms of increasing energy level, you're not going to go to the one that's a higher energy level first, right? That takes too much work. You're going to fill up this guy first and then fill up that guy. Okay, so. Okay, so let's do a quick refresher. So we have, what are the subshells? And since we've been talking about them already, you guys should help me out here. So the S subshell, the P subshell, the D subshell, and the F subshell. How many electrons can the S subshell hold?
2.
Okay. What about the P subshell?
6.
The D subshell?
10,
The F subshell?
15,
14.
14. Why is it 14 and not 15?
I don't know.
Anybody? Anyone? Because you guys don't.
The wide periodic table.
What was that?
The wide periodic table you showed us last time.
Exactly. Because of the wide periodic table. If you look at it, hold on. Let's see. So here's our periodic table, right? So these last two, 71 and 103, these guys really belong in the d orbital, right? So they're just a spot, they're a placeholder. 71 and 103 is a placeholder. So these guys are all in the F, right? And if you pay attention to the atomic number, it goes 55, 56, then it goes down to 57, 58, 59. So from here, to there, those are all in the D subshell. These guys are in the F. These guys are in the F, these are in the D. It's obviously a Monday if you can't tell. So these two are D. You guys get that? You see it?
Yes.
Yeah. So it's just holding a spot, okay? Or we can look at the wide one and it actually shows it nicely, okay? Piece of cake?
Piece of cake.
Good, good. Okay, so here's our next part. So we were talking about the number of electrons. So if okay, because our limited knowledge of the elements, right? So we only know about the elements that are on the periodic table. There's the possibility of getting more and more elements. So that means that there's the possibility of keeping track of those electrons as well too. So in that case, we would have our next subshell would be G and H. If there were more and more elements on the periodic table, we'd be able to go into those into those subshells. So I'm going to go through and I'm going to explain something to you, and then I want you to think about it a little bit, and then answer to me how many electrons do you think the G is going to have, and how many electrons do you think the H is going to have, okay? So when we talk about orbitals, orbitals is the actual route that the electrons are taking. And each orbital, you can hold 2 electrons, okay? So if that's the case, how many orbitals does the S subshell have?
1,
Okay. What about the P?
3,
The D?
5,
The F?
7,
The G?
9,
The H?
11,
11,
Okay.
and
So
13.
then how many electrons would you expect G to have, or G to be able to hold?
18,
And then H?
22.
Piece of cake?
Piece of cake.
Good. This is fun. I get to see who never reads their emails. Yeah, so we had to go to passcodes. I forgot to tell you that. So Zoom's policy now is that you have to have a passcode for your meetings, for all your meetings. So you guys all know the passcode is always going to be CHEM-101. So
Yes.
for all of the meetings, you shouldn't be able to forget it. So. Okay. Okay, so pretty simple so far.
Yes.
Okay.
Yes.
Good. So let me give you a little more info. Okay, so we talked about the orbitals. Let me show you what they kind of look like, right? So you kind of get an idea. So this is essentially what Bohr's model looked like, and basically you have these beautiful orbits that are going on, but reality you get this really condensed, crazy-looking cloud structure that goes on. The reason why it's so crazy looking is because you have all of the different types of orbitals that exist. So for the S, you have that one orbital. This is the S orbital right here. The P has 3 different orbitals. You have the PX, that means it's on the x-axis, and you can see it's like a dumbbell or 2 marshmallows stuck together, right? On the y-axis, PY, and then on the z-axis, right? So these are 3 different orbitals that the electrons take. 2 electrons go in each one of those orbitals. So this is the D, right? So we have dz squared, and you can kind of see it's on the z-axis kind of crazily. And then we have dx squared minus y squared. So basically that means it's going to be on on the x and the y axes. This one is dxy, that's between the x and the y axes. And this one is yz, again, between the y and the z axes. And this is xz, between the x and the z axes. Okay, so again, 2 electrons in each one of these, right? And so that kind of gives you an idea that like how the routes are kind of crazy with each other, right? And it's kind of, as I said, a little crazy. Okay, so if we go to the multiple levels, right? So the 1s is going to be closest to the nucleus, right? It's going to be real tiny. The 2s is going to be a bigger one. The 3s is going to be even bigger around it. So that means that the outer shell is always going to be that higher period, okay? So Pauli exclusion principle basically says that you can only have, at most, in an orbital, 2 electrons. So you could have 0 electrons, you could have 1 electron, or you could have 2 electrons. You can never have like 8 or 25 in a single orbital. Okay, you guys get that?
Yes.
Yes.
Okay. So there's one other thing that I wanted to talk to you about. So there is the Hein principle. So if I have 3 orbitals, these are my 3 orbitals. This is going to represent, these 3 spots are going to represent my 3 orbitals, right? So let's say this is, if it has 3 orbitals, which subshell am I talking about? Or sublevel I'm talking about? Let me repeat that question. Which sublevel am I talking about if I have 3 orbitals?
P.
P, thank you. So we're talking about the P sublevel, right? And let's say we had a total of 5 electrons to put into the P orbital.
Oh, I get it now. Sorry.
Okay, so if I have 5 electrons to put in the P orbital, the way that I would put those in, I'd put 1 going in one direction. This one would get filled next. This one would get filled next. Then I'd come back and fill in the other direction. Okay, so if I was putting in just 3 electrons in the P orbital, the PY, I mean the PX would get 1, the PY would get 1, and the PZ would get 1. You will never have a case where you do this. Okay, why do you think that? Why do you think that happens? What is the logic? David? Are you there?
Yeah. The logic
Yeah.
for the little diagram you drew on the bottom?
What was that?
Did you say what's the logic for the diagram you drew in the bottom, like the 2
Yeah.
electrons on?
Yeah, so why wouldn't we do this? Why do you think we wouldn't do this?
I'm guessing the uneven distribution, since there's 3 orbitals, we want an electron each.
Okay, that is actually a good thought. So let's think about it. If you guys came in and there were 3 love seats in a room, and 3 of you guys came in, would 2 of you guys sit in the same love seat and just leave 1 love seat empty?
No.
No. Why? I mean, okay, let's make a couple of assumptions, right? Let's assume that you guys aren't dating each other, right? That's usually a key to it. You're all single and you don't like each other that way at all, okay? So why don't you guys sit coupled up like this? So these are 3 love seats. So why don't you guys, 2 of you guys, sit together in the same love seat?
Because we want all the space we can have, so we want our own love seat.
Exactly. And that's exactly what happens with the electrons. The electrons want all the space that they can have, right? If they're forced, if there are 6 of you guys, you have no choice, right? So then you guys will couple up in seats, right? So it's just like your personal logic is the same personal logic that they have, okay, in a sense. They need their space, okay? So do you guys see that? You understand it?
Yes.
Okay, so this guy
Yes.
won't happen. Instead, we'll do this. Okay?
And I see how the arrows are all going up. Would there be an instance where the arrows would all be facing down, or is that just how we start for each orbital?
That's typically how we start for each orbital. So what's happening really is that they're going, the next one is going to be going in the opposite direction. So they're opposite spins of each other. One spins one way, one spins the other way. So it kind of like counters the energy level. So then that way it keeps the energy low. If they're spinning the same way, it puts up too much energy. It excites that orbital, or that, yeah, it excites that orbital and it kind of pushes it up, which is not what we want to do. We want to try to keep a low energy profile. By them going opposite of each other, then the spins being opposite of each other, it keeps a lower energy profile. And so the electrons are kind of like this. They're really like us in ways that if they don't have to do any extra work, they're not going to do extra work, right? So if I told you, all you have to do is come in to the Zoom meeting and say, hey, what's up, Dr. Henry? And give me a smile and a fist bump through the screen. What would you do?
Power them. That's all I do.
Okay, that would be all you do, right? So the electrons are very much the same way. They don't want to do any more work than they would have to do, bare minimum, right? Because they want to keep a low energy profile, just like us, right? There's many other things that you could be doing. If you know that you can guarantee get an A, just to come in and say, give me a smile, you would, I mean, I would get you guys to smile all the time. I see your faces, you know, that whole 5 minutes that will require you to come in and say, hi, what's up, you know?
Okay.
Even the shy ones.
Thank you for the analogies. They really do help.
You're welcome. Okay, so let's move on. Okay, so we've already talked about electron configuration, and this is just a little map of everything that we talked about in terms of the order. And you guys see the 3D down here, and so, and the 4D, 5D, 6D, and then the F subshell, okay? So this is just showing you the electron density map. And so this was actually monitored of the electrons en route in one of the orbital structures. So this is just showing you what we've talked about in terms of the organization, the principal number, the sublevel, how many electrons are in that sublevel, okay? This here is just giving you a quick sheet of the ground states for all of these electrons, and you can see you have your core, and those would be the electrons available for reacting, okay? So let's go back to the periodic table and see what we can remember. Okay, so let's do.
Ooh, wait, I have a question.
Yep.
Sorry. Just really quick, back to what we were doing with the whole orbitals, keeping one electron in each orbital. So if we were to do 4 electrons in those 3 orbitals, would you do one up arrow and down arrow in one orbital, and then an up arrow in each of the other separate
That's right.
orbitals? Okay.
Yep.
All right. Thank you. That's all.
Okay. So let's do, we're going to do arsenic. And we're going to do PA. Okay, so what is the electron configuration for arsenic?
So 1s2.
You guys want to do the 1s2?
Yeah.
So you guys want to go, you don't want to do it the easy way.
I'd rather do it the easy way.
Fine. Easy.
Okay, so here's arsenic. I mean, we can do it. I mean, we can go through it, do it the hard way, but where is the nearest noble gas?
Argon?
Argon. Okay, so then we're saying that all those electrons that were there That's what we've already accounted for. So then we go down here. So then what's after argon? We have what?
4s2.
Okay, so that gets rid of here. So we've already covered these already with the argon, right? Okay, and then
3d10.
what was that?
3d10.
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 Okay. 3. Okay. So that gets rid of this.
It's 3. Yeah, 4p3.
Okay, piece of cake.
Yes.
Yes.
Okay.
Can you make one complicated like the other one?
Oh, I will. Don't worry.
Okay.
We're
Like
we're
that's what I
building
need
up.
help with.
Yeah. We're building up. We're building up. Okay, so let's do PA. We'll do this one in pink. So for PA. Okay, where are we going to start?
By
Cheyenne.
finding it.
Finding it. Yeah, that's always a good start.
Mhm.
Okay, so where's PA? Help me.
All the way in the bottom. 91.
91. Okay, so it's right
Okay.
here.
Yes.
Okay, so what is the nearest noble gas, Cheyenne? Are you there?
Yeah, sorry. Is it radon?
That is correct. So we go back up, and the nearest noble gas is radon. Okay, so we know that we got all of these covered from the very beginning to here, so we're going to just mark them out. I'm being lazy and drawing a little crazy X there. Okay, so then we'll just put bracket, radon. Okay, so then what's following after the radon? So that brings us down here.
7s2.
7s2. And then
Would that one, can anyone answer?
Yep.
I guess, would that one be considered F? Didn't we just talk about that one?
that's right. So we go
Yeah.
down to the F. So what would be the F?
Maybe F2.
What F? 1 F, 2 F, 3 F, 4
2
F,
F.
5 F. 2F?
2F3?
Nope, not 2F.
5F.
It would be 5F because remember we're starting at 4F here. This is 4F.
Oh, okay.
Yeah.
Thank you. 5F.
5. And 5F3. Okay, piece of cake.
Yes, sir.
Okay, so let's do something that's challenging. These are too easy, right? Make it a little bit harder. So we'll do goal.
Wait, I'm sorry. So why I don't know how to pronounce this, but why isn't oganesson a noble gas, but radon is?
So oganesson is not a true element. That's the reason why it's in gray. It is it's a man-made, not truly stable. It doesn't last long enough to be considered an element. So we don't know if it would be a noble gas or not, for one thing. The other thing is you don't use that as your core because you want to go with the noble gas that will be before
Oh,
the proactin.
yes, yes, of
Proactin.
course.
Okay. So let's say we had gold. We're going to go gold, and then we're going to do gold's ion. We're going to do gold 6+. So we'll do AU, and then we'll do AU 6+. Okay. Okay, where do we start?
Krypton.
You said krypton?
Yeah, Krypton, the nearest noble gas.
So AU is here.
Oh, my bad.
Xenon.
Okay.
Yeah, xenon.
Okay, and then
6s2.
okay.
5d8. 5d9. My bad.
Are you sure? That's where we're gonna go next.
It'd be F, right?
Yep.
Before F.
Or F.
15, you said, right?
For F, not 15.
14.
For F 14.
Oh, yeah. I haven't had it written down.
And then you said it would be the 5D. And you said 5D what?
5d9.
Okay, piece of cake.
Yeah.
If you don't forget the 4F, right?
Yeah.
Yeah. Okay, so now let's look at the ion. So now that we already have it drawn out, what are we going to remove, and who are we going to remove from first?
Oh.
The 6s2.
So that's right. So we'll go. So you don't want to break your core. So you always want to try to keep your core. And then you set the 6s2. So that's the first one to go. Okay, so no 6s2. Okay, so then that's 2 electrons. We have 6 to get rid of total. So then what am I going to take away from next?
We take the other 4 from 5d9.
Okay, so we'll have 4 F14, and then it's 5D 5.
5d5. Yeah, because we take 4, right? From the 5d9?
That's right. Yep, that's correct. Yeah. Piece of cake?
No, I'm confused. Sorry.
Okay, so
I hope I'm not the only one.
You're not, don't worry.
Okay.
okay, so here this means we're removing 6 electrons. You see that 6 plus?
Yes, because
Okay, so that means we're 6 electrons.
yeah.
2 of them are coming from here, so we're getting rid of, let me put this in a different color so you guys can see it. We're getting rid of this guy because this is the highest period, right? Isn't 6 higher than 4?
Oh, okay, I get it now. Sorry. I was so focused on the S's and the F's and the D's. I was like, wait, why would he get rid of a D if there's an S if there's an F and a D in front of it? But it's
You have to pay attention to, because remember, I told you that a long time ago.
Yes, you did.
These are the energy levels, right?
Yeah.
And so the higher energy level. So you want to get rid of the higher energy level first.
Which is
you want
6.
to try to keep a low profile, right?
Okay, that's what I thank you. I'm
Yep,
good.
and then
I
the
don't know
rest of
if
them-
Norma, are you still confused?
No, he cleared it up. I was like,
Yeah.
I was kind of focused the same way you were.
Yeah. Okay. All right. We're good then. Thank you.
Okay. Piece of cake?
That is on.
Pretty
Now
good,
it
yeah.
is.
Okay. Sorry, I'm a little hoarse. So my general chemistry class, I had labs this weekend, and so I was just yelling the whole time. Not because they were doing anything bad. It was just we did part of it outside, so I was yelling outside, and then I had to come in and yell in the inside, and so So I'm a little hoarse right now. So.
Oh, I thought it was because you went to a rave and you're screaming and yelling, partying, you know.
Yeah, you know.
Just teasing.
No, it's okay. I would love to. I mean, as soon as COVID is over, I'm gonna party really hard, let me tell you. Okay. Okay, do you want to try one more, or do you guys got it? You don't need any more help.
One more, just in case.
Yeah, one
Okay.
more.
Let's see. Let's make it good. Let's do. Let's do lead. We'll do lead and lead light. Lead and lead 8. So.
What if you are adding electrons? Then you would just go through the same process.
Yeah,
Or
you go
no?
through the same process, but adding is always the easiest part because then you just go in order, right? Removing is the harder part. So let me give you an example of adding. So let's
Okay.
say we have. So tellurium 2 minus.
I always have to take like a minute to find it on the table.
All right, that's what it's going to be like in the beginning, but then once you get to it, used to it.
Okay, I found it. So you would start off with krypton. Correct?
That is correct. Okay, and then
And then it'd be 6s2. No, sorry.
5s.
5s2, yes.
okay,
And then 4d10. And then it would be 4p4.
you sure it's 4p?
Well, now I'm not, I guess.
5.
Oh, 5.
Five.
Yeah, 5.
5p, how many?
5p4.
It's 2 minus.
Oh, I thought we were doing the same process before
Oh,
where
so if
we did
you
it.
wanted to do tellurium first, that's fine. We could do that. I'll just put it down here.
I think that's kind of like maybe the best thing to do so we can see the difference. I'm not sure.
No, that's fine. And that's what most people do. They'll write them both down. Okay, so then for tellurium 2 plus, then how many are we adding? I mean, what are we doing?
We're adding 2 electrons.
So we're adding 2 electrons. So if we have 5p4,
It would be 5p6.
okay. Let's see if I can get that 4 to move. Okay, piece of cake.
Yes.
Or I could have just written it as, let's see. As just xenon, because if it's 5p6, it's a noble gas. So if I could just use that as a core. So this brings me to my next topic. This is called isoelectric. Or sorry, isoelectronic. Isoelectronic means the same number of electrons. So Te2 minus has the same number of electrons as xenon. Do you guys see that? So if I added 2 electrons to this, 1, 2, I have xenon.
Yeah.
So does this apply to when we're removing electrons?
You said yes, this does apply to when you're removing electrons or gaining electrons. You could have the same number of electrons, yes. So anytime iso meaning same, electrons, electronic meaning electrons. Questions?
I'm fine. I don't know about anyone else.
Okay. Silence means perfect, or
Yep,
nobody
we're
knows?
good.
You're
That
good?
makes sense.
Okay.
I came in
So-
really late, so I'll just be watching the lecture from the start.
Okay.
So I guess to be sure on my end, to make sure I really do understand it correctly. So for example, the one you just gave us, the Te2 minus, if it was Te1 minus, it would be iodine?
That's right.
Okay, gotcha. So, and if it was like Te plus 1, it would be, what is that, antimony?
That's right.
Okay.
Yeah, so it's not that it's that, but you wouldn't put it in brackets that way. You would actually have to do the electron configuration, just showing you that they're exactly the same number of electrons. You can use the brackets means that you have that core filled.
Okay.
You understand?
Mm-hmm.
So. Okay, let's see. So, are you guys feeling comfortable with electron configuration more so than when we started?
Yes,
Yeah,
sir.
more
A
so.
lot better.
You had me sweating there for a minute, I'm not gonna lie. Like, I know I talked about this.
Sorry.
It's all right.
I sometimes get distracted with my little one and miss like 5 minutes or 10 minutes and then come back
Yep.
and I'm like, what?
Yeah, if you blink, you've missed, a lot of great information.
Yeah.
So this again is just telling you the core concept of it, So in this, we've already known how to write the electron configuration. So let's do, okay, so let me tell you about some exceptions, okay? So there are some exceptions that do occur. The book only talks to you about 2 of them. And let me explain to you why they occur the way they occur. I won't require you to remember the exceptions. If you can just write it down based upon the periodic table, I'm cool with that. Because at the level that you guys are at, you don't need to. But if you're in my general chem, you'd have to remember the exceptions. But I'm going to tell you about them so you know. And if you do get them, you may get some extra points thrown your way. Okay? You guys ready?
Yes.
So your 2 exceptions that that the book talks about is this guy and this guy. Okay? So what happens in the case of chromium? Chromium has 1, 2, 3, 4, right? So it likes to have what we call a stable subshell, or what is the word? You had mentioned it earlier, equal distribution. It likes to have equal distribution. And the energy level between the 4s and the 3d, now they're very little, there's a very little difference between those 2. So this will be the 4s. Let me make it in a different color. so it's clear that it's a. Anybody colorblind?
No, not me, at least. I don't know about anyone else.
No.
No.
Good, good. I like that. Makes it easier so I can still use the colors. And although even if you were colorblind, we'd work with you. We'd make it work. So this here is your d orbitals, right? So this is that. When we break it down, that's your d x squared y squared. This would be your d xy. This is your d yz. Your d xz. Oops. And then your d x squared y squared. Okay. So these, in this case, you have 1, 2, 3, 4 electrons, right? So what it'll do, because it likes to have equal distribution, if it could get equal distribution where you have 1 electron in each one of the Ds, it'll actually borrow from that S. So then it'll put 1 up here, 2, 3, 4, 5, 6. So it'll actually borrow from this guy to fill in the rest. So there'll be a nice equal distribution. Okay, so that's what's happening in the case of chromium. It also happens with mobidium and a little bit with tungsten. Tungsten is kind of a little weird one because you also have this orbital down here. Okay. So do you guys kind of see that?
Yes.
Okay. So in the case of copper, it does the same thing because in this case, you have coppers like this, where you have the one that's going down. Sorry about the backwards down. So it takes from the 4s so that now you would have equal distribution in your d orbital. So it'll fill up that d orbital completely, leaving 1 in the 4s in the case of copper. And it does the same thing here with silver. And gold, again, is a little funny and how it does it. Okay? So if you remember that, great, you'll get some extra credit point. If you don't remember that, then it's okay, right? I just want you to kind of get the general pattern and stuff. Okay? Piece of cake, simple.
Yeah.
Mm-hmm.
Okay. Okay, so can you guys write the electron configuration for chlorine?
Chlorine.
Mm-hmm.
So then the noble gas would be neon.
Okay.
That is closest to before it. And then it would be
3s2.
3. Mm-hmm.
Four P5. No, 3P5. My bad.
Okay, so this allows me to talk about one other thing. So when we're starting to talk about our electron configuration, this is kind of setting us up for what we call the Lewis dot structure, right? So if you guys look at it, the noble gases, particularly in this first row, it has a total of 8 electrons in that period, right? You count 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the noble gases are stable because their octet, they fill that outer shell completely. So all of the other electrons want to be like those noble gases. They want to fill that outer shell. So that's why we either take electrons or we give electrons or we share electrons. Okay? And you guys get that so far? Take,
Yes.
give, or share. Okay? So in the case of chlorine, how many what we call valence electrons do we have?
7?
7. So to draw the Lewis dot structure for chlorine, we would use only the valence electrons because those are going to be the electrons that are going to be involved in chemical reactions.
Okay.
So it has 7 electrons that it can use to be involved in chemical reaction.
Sorry. Mm-hmm.
So we would draw 7 dots around our symbol. And this is the Lewis dot structure or the Lewis dot symbol. It's called both actually in this textbook. So, okay, piece of cake.
Piece of cake.
Okay, so now here's the deal about the Lewis dot structure is we're basing it upon the octet. So remember when I told you a while back we only use the main group, right? In a long time ago, where the main group consisted of just these, this one, and all of these over here.
Does it
And the
matter where you
more-
put the dots?
It does because you want to form like, it doesn't matter which side you on. Like, so for instance, I could put the 1 over here and then put 2 over here, or I could have put the 1 here and put 2 here. So it doesn't matter where that 1 goes in terms of its location, but you kind of want to have pairs of electrons going together. If you can form pairs, you want to have pairs because electrons are going to be paired up in those subshells, right? Or in the orbitals. And so you're kind of saying these guys are paired up, or you have them in orbitals. Now, they could be used still if we need to use them, right? But if you don't need to use them, they're going to stay in that subshell.
Gotcha. So are these kind of just the same way as the love seats, where if you only had
Exactly.
4, you'd put 1 on top, 1 on the bottom, 1 on the side, and 1 on the other side?
Exactly. Yep. Like carbon, right?
Okay.
So carbon is a good place. And I did show you the, did I show you guys the movie? Carbon's a Horde. Chemical
you say?
Party. Did I show you guys the little movie, Chemical Party?
Yeah.
Okay, good. Okay, so yes, so carbon can form 4 bonds, right? So that means you have this electron that it can form 1 bond with, or share an electron with. This one it could share another electron with. This one it could share another electron with. This one it could share another electron with, right? So that's why we put it in those 4 distinct locations in the case of carbon. Okay, so as I was saying, we kind of ignore the transitional metals because transitional metals are a lot more complicated in terms of their bonding capability. They will bond, and in most cases they form ionic bonds, right? But it's a lot harder to understand in terms of that Lewis dot structure, okay? So we basically look at the Lewis dot structures of our, of the ones that have the red lines in front of them, the main group, okay? And so we always look at it in terms of the outer shell. So when we're talking about our Lewis dot structure, we typically look at the s and the p orbitals, because if you count what's the maximum that you could have in the s is how many? What is the maximum number of electrons you could have in the s orbital?
2.
Yeah.
And how many can you have in the p orbital?
6.
6.
Altogether, that's going to add up to what?
8.
8.
8. So that concept of the octet, we want to try to get to our octet. That's because your s and your p orbitals are full. You look at that, if your s and p orbitals are full, you're a noble gas. You guys can see that?
Yes.
Okay. So that brings us to Lewis dot structures, as I was mentioning. So if I have oxygen, what would be the Lewis dot structure of oxygen? Where's oxygen located? You can give me the atomic number.
8.
8.
Okay. How many valence electrons does oxygen have?
6.
6. So then that means I would put 6 dots around my oxygen molecule. 1, 2, 3, 4, 5, 6. Piece of cake?
Yes.
What about silicone? How many valence electrons does silicone have? Again, just looking at the S and the P.
4 valence electrons.
Okay, so how would I draw that?
1 electron on the top, 1 on the bottom, 1 on the right, 1 on the left.
Okay. Let's say we have germanium.
4 as well.
Okay, so then that would just GE. 1, 2, 3. What about bromine?
7.
Piece of cake?
Yes.
Okay, so if we go to the other side, let's say we have calcium, Ca.
That's only 2.
Okay. Okay. Now, if we're talking about ions, let's say we were talking about calcium 2+. So all we would do is write it as, it would be losing 2 electrons, so they would be gone. So we would just write it calcium plus in brackets. If we were talking about silicon, let's say 2-, Si, 2-. So what would we do in that case? Actually,
Wouldn't you
bracket.
add
Brackets SI minus.
Sorry, the brackets should be, the plus should be outside the brackets, my bad. So where would I draw the dots? That's what I'm asking. So you're right, there's going to be brackets, 2-, and then where would I draw the dots? For silicone, how many dots will I have and where would I draw?
You have 2 dots left?
I would have 2 dots left. Just this.
Oh, no,
But
no,
it's
no.
2.
You have, yeah, you have 6 now.
I have 6 now. Oops. That's a dot, not a 4. Yeah, erased everything except the dot there. Okay, piece of cake.
So what are the brackets for?
The brackets is to remind me that it's an ion. And then this tells me the charge of that ion. Okay?
Yes.
Okay. Okay, so let's move on. Yeah, 15 minutes. I think we're gonna finish this chapter. Okay, so you guys feeling pretty comfortable with electron configuration overall? Yeah, no, maybe?
Yes.
Yes, sir.
Skip over this. We've talked about valence electrons. And you guys understand the electrons that are going to be involved in bonding are considered your valence electrons, and you're going to be looking at primarily your S and your P.
Yes.
So this is just showing you the Lewis dot structure of the different groups. So here's your 1A group. That's your primary group, not your primary, your main group. This here just gives you the IUPAC group, the 1, 2, 3, 4, 5 up top. So this lets you know the Lewis symbol for those elements that are there. So let's get to some conceptual questions. So it says, write the electron configuration for the highest occupied energy level for group 6A16. So it's the sixth group 16. So generally what they're saying is you want to write a generic form so that it could get any number, it could keep going up as much as it wants to if the periodic table expands beyond just the 7. So we'd use, when you're using as many numbers as possible, you would use, or let's say you have, when you have infinite number of variables that you're adding to it, we put what letter. Like if I'm talking about X can go to any number that I want it to go to, I usually use something like n, X to the n power, right?
Yes.
Okay, so if I can go to any period that I want to go to, I'm going to write this for group 16. What is the general form for group 16? How many electrons do I have in the S? How many electrons do I have in the P?
2 and 4.
2 and 4, right? So then I would write this as n, meaning any variable, right? S, and you said there was 2,
Mm-hmm.
and then n, P, 4. Okay, so identify the group whose electron configuration for the highest occupied energy level is N2, NS2, NP2. So what group would that be?
Wait, I didn't hear what you said. Can you please repeat it?
Identify the group whose electron configuration for the highest occupied energy level is NS2, NP2.
Would it be the, how do you say it? Chalcogens?
It should be. Think about how many, look at it, if we're going 2 electrons in the S, and then if we have 2 electrons in the P, what group would that be?
Oxygen?
Are you sure? 2 electrons in the S and 2 electrons in the P?
1, 2, 3, 4.
No, that's where carbon's at.
Okay, that's where carbon's at. So which group is that? What group number is that?
Group
14.
Yeah.
Group 14. So they want you to identify, it says identify the group.
We'd still be right if we wrote group 4A though, right?
Yeah, if you wrote group 4A, that would be right too. Or if
Okay.
you wrote group 14, you'd be right. Okay, if you guys see that, 2 electrons in the S, 2 in the P. So let me pull up the periodic table. Clear. So they basically just asked us which group would it be if we have 2s filled and we have 2p filled? What group would that be? So these are filled and these are filled. So these are your groups, remember. So it would be for group 14. Okay, so if I had NS2, NP1.
Group 3A.
Okay. Or
Group 13.
Yeah.
okay, piece of cake.
Yeah, why am I still confused on the NS2 NP4? I don't know why. That first one just threw me off.
I don't know what. Did you say
Because then-
NS2? NS2.
It has 2 in the S
Okay.
subunit.
So that's 1, 2, and then if I have 4 in there, 1, 2, 3, 4. So what group is
Yeah.
that?
It would be the 16.
Yeah.
Why did you guys say it was 14 earlier?
That's because it wasn't NS2, NS4. It was NS2, MP2.
Oh, okay. I probably just didn't hear your question correctly. That's why. Okay, then I'm good. Thank you.
Yeah.
Appreciate
I have a question though. I get why I get the placement of like group 16 and like 14, but I don't get the 6A and 4A. I don't understand that. Like why they're labeled as that.
Because you have what we call the main group. Main group consists of the ones that don't include the transitional metals. So for instance, this here is 1A. This is group 1A. This is group 2A. This is group 3A. This is group 4A. So those are considered your main groups because we used to ignore. They wouldn't count these. They wouldn't even look at them, right? Because all of the chemistry that we were doing was all only involving these guys. We would avoid the transitional metals because we didn't know enough about it. So they were ignored early on. So they would have what we call the main group, and then this would be the subgroup or the non-main group, right? Down here. And then they would start with B instead of an A, right? So that's where you get your group A and B. So the old periodic tables, a lot of the older periodic tables have what we call a main group and a non-main group, and that's group A. I mean, that's where you get your 1A, your 2A, your 3A, your 4A. And if you just look at it, it's the goalposts. The goalposts are the ones you're going to be counting in your main group, right?
Okay.
Goalpost, okay? So that's just one way of remembering it. Now, I don't care about the main group because we look at the periodic. We care about the IUPAC group because that's the one that's used internationally. The main group is only used in the US, and it's typically used by people who are, I'm going to say, about 70 plus years old, okay? Well, it's true. I mean,
Yeah.
I'm being truthful here. So a lot of the older chemists will still use the main group, you know?
Okay, thank you.
So that's why you'll see it written as 4A/16 group 4A/14.
Gotcha.
So, yeah, because it's both. Yeah. Okay. Questions, concerns, Cash,
Pieces of cake.
pieces of cake. Excellent. So we've talked about octets. Okay, so let's talk about some quick trends. Then we'll stop there. We'll talk about the first one. And we'll pick it up on Wednesday. So some of the trends that we notice is trends in atomic size. So as and it'll make a little sense if you kind of think about it a little bit, right? And I want you to think about it a little bit. Okay, as we go from left to right, we're going to get smaller. Okay? So the size of the atom gets smaller from left to right, and the size of the atom increases from top to bottom. Okay, so let's look at the periodic table. Oops. So here's the periodic table. So as we go from left to right, it's going to get smaller. Now, you've got to remember that where are all the positive charges?
On the left side?
No, in the atom. Where's all of the positive charges in the atom, not on the...
Oh, the protons.
Yeah, so where are the protons located?
They're inside the
In the-
nucleus.
They're inside the nucleus. Where are the electrons?
They're outside orbiting around.
Okay, so if you have positive charges on the inside, what happens if you have a whole bunch of positive charges on the inside and then your electrons on the outside? What's going to cause that electrons to do?
I'm not sure, to be honest.
Neutrons.
Think about a magnet. So if we had a magnet and we had all of plus, right, on the inside, right? So these are all plus in the middle here, okay? So then out here we have, let's see, we have our electrons circling it, right? So these are all negative out here, right? So if I put more and more stuff in the middle, what am I going to do to that stuff on the outside? What's going to happen?
Is it going to pull it towards the nucleus?
That's right. It's going to pull
Okay.
it towards the nucleus. So the more and more positive charges you get, the more you pull that stuff towards the nucleus, right? So what's happening as we increase our atomic number?
We're increasing the number of protons? Is that
We're increasing
correct?
the number of protons. So are protons positive?
Yes.
And remember, this is kind of being held, the protons in the middle, it's kind of being held stationary. It's like it's in one spot where the electrons are constantly moving around. So that orbit, the orbit of those electrons are being pulled closer to the nucleus. So the more and more protons you have, the smaller you're going to get, right? So
Okay.
as I increase from 1 to 2, I should be getting smaller, right?
Mm-hmm.
As I increase from 3 to 10, I should also be getting smaller.
Mm-hmm.
Okay, so that's the reason why the size is it's going to decrease as we go from left to right. Okay, so size decreases okay. So have you guys ever seen the Russian dolls?
Yes.
Yeah.
You know, the little dolls where they put another little doll and then another little doll and then another little doll. Okay,
Mhm.
so that's kind of like the periods. The periods are just putting, you know, electrons outside of electrons, outside of electrons, outside of electrons. So it's the Russian doll theory, right? So the 1s is smaller than the 2s, is smaller than the 3s, is smaller than the 4s, is smaller than the 5s, is smaller than the 6s, is smaller than the 7s. So size is going to increase as we go up or down.
Down.
Yeah,
Right.
that's
As we
good.
go down, size is going to increase. So it's going to increase as we go down. Okay, so now I'm going to ask you a really hard question. Okay, you guys ready? So who's
Yeah.
going to be the biggest atom on the periodic table based upon these trends? So its size decreases from left to right, so it gets smaller this way, and increases as we go from top to bottom.
Would it be francium?
That's right, it would be francium. Francium would be the biggest electron on the periodic table at this point. So who would be the smallest?
Hydrogen.
Helium, right?
Lithium.
Helium.
No, helium. Wait, I don't know.
Helium would be the smallest. Smallest? Biggest. Okay, you guys get that? You see that trend?
Yes.
Yes.
Okay. So we will stop here and we will pick this back up on Wednesday.